And now I explain the wave's amplitude. Wave's amplitude is defined like 2 times this h, where h is I defined before, and h depends. Well, we suppose that it depends explicitly and only on the quadrature. Well, the two derivatives on time of the quadrature. What is the quadrature of what is Q related? Q related with the symmetry or with the antisymmetry. Because, well, if Q is 0, it's because the space is symmetrical. For that, Q is related to the energy, the kinetic energy, asymmetric. And we notice that that this has units of mass. Then we can make an example, and well, suppose that is has the solar mass. The object is 54 mega light years, and the length of our device, the length of the arms of our device, is around 10 kilometers. Then we obtain that the elongation or the difference between the final length and the initial length is around this quantity. It's small, comparing, for example, with a radius of a proton that it is around 10 power minus 15. It is 100 times smaller than the radius of a proton. It's so small. And well, the polarization. The waves can be polarized in X form and in plus form. This example, we have a ring of particles. If a gravitational wave incides over this ring, the particles oscillate like this or like this in function of the polarization of the wave. In this case, it oscillates in plus form. In this ring incides plus polarized wave, and in this in cross form. And well, seeing this motion, we are able to know the polarization of the waves, and knowing the polarization of the waves, we can obtain directly inferences about the properties of the source. Well, and now I will explain the differences between gravitational and electromagnetic waves. And then, well, I divided it in some difference. Well, for example, for the propagation medium, or the medium. In electromagnetics, is the space. In gravitational, is the space-time due to the general relativity. The sources are different. For example, electromagnetic, it's the incurrent in the superposition of atoms and molecules. In gravitational is the current movement of grid mass. The wavelength in electromagnetics is small because frequency is high. And well, in gravitational is the inverse. Normally the wavelength is, well, normally no. Normally is greater than the wavelength in electromagnetics because frequency is slower. The interaction, electromagnetic interacts with the matter. The gravitation practically doesn't interfere. Does not interfere with anything. It doesn't interfere because with matter the wavelength is so high that practically does not interact with matter. And the detection forms in electromagnetics, in gravitation, in gravitational waves are different, because we detect in case of light of electromagnetic waves with wavelength small, we detect it with the power of this light. And the gravitational, always we measure the amplitude, the edge. And well, I begin with measure devices. The first one is the Weber bar. It's the first one in 68 Webers to it. It consists of many cylinders of aluminium with dimensions 1 meter of diameter and 2 meters of tall, at temperature approximately to 0 Kelvin. It has an antenna form. And vibrates 1616 Hz, and could detect deformations about 10 power minus 16 meters of around of 10 electrons. And the mini grail is the most important of this type, but with the particularity that it has a spherical form, and for that it's able to detect all gravitational. It's able to detect all gravitational waves independently on the polarization. Why? Because in the others, in cylindrical form, only it's capable to detect the gravitational waves coincides over the basis of the cylinder, while in the spherical form, all the sphere is the basis, is the detector. And well, the characteristics are that 68 centimeters, 1,150 kilograms. That resonates at 3,250. It works at 20 millikelvin. Well, it is isolated from vibration by 140 kilograms masses. Can detect oscillations around 10 to minus 20 meters. The 100th part of an electron, or 100 times smaller than an electron. This is the mini grail.